Hi, my name is Linda Ortiz, and this is my video lab report for Lab 1, Constant Velocity. For Lab 1, I observed constant velocity is represented by a person riding down an escalator. In other words, a person that is moving at a constant speed without a change of direction. The goal of this lab is to prove that F of net, the net force, is in fact zero when constant velocity is present. Newton's second law indicates that when the net force on an object is zero, then the final velocity will stay the same as the initial velocity, hence constant velocity. The steps I took in order to gather sufficient data for this lab are as follows. Step 1. Capture video of the motion. Step 2. Analyze the video using Tracker. Within Tracker, I specified the video frames, in this case 75 frames total. Next, I specified a time step of 0.033 seconds. After that, I used a calibration stick to specify the length of my person in meters. And finally, I set up the coordinate system so that the person was moving along the positive x-axis. Using point mass, I was able to follow the motion of my person on Tracker and extracted data that I would later use to plot the observed position versus. Step 3. Construct a computational model describing observations based on physics principles. Using Python code and idle, I was able to construct a computational model. I updated code that was provided so that the simulation would provide me with the data needed to plot the predicted position versus time. Here is how I updated the code. I specified the mass of the ball, the representative of my person, and then specified the initial conditions, including the initial position and the initial velocity, as well as the beginning time of 0 seconds. Next, I specified the time step. After that, I updated the ending time. Since the code provided didn't apply to Newton's second law, I made sure to update that as well, which involved a statement for velocity, position, time, and net force. As you see as I run the simulation right now, you can see that the graph is linear, the ball is moving in the positive x-axis, as did my person down the escalator, and it's quite similar to my real-life video. Step 4. Compare the data observed from both my video analysis and the data from my computational model. Now it is time to compare data from my video analysis along with data from my computational model. I plotted the two graphs over each other. The blue dotted line you see represents the observed position versus time from the video, and the red line represents the predicted position versus time from the computational model. As you can see, the two lines are practically the same, but there are moments when the blue dots veer away from the red line. This error is involved with my placement of point mass earlier on when I was using Tracker. As the character I used for the video was a person instead of an everyday object, like let's say a ball, I was unable to simply place point masses within the center of my object. Nonetheless, the goal of our lab is proven here, with the two graphs overlaid over each other, that the constant velocity is present when the net force is zero. Step 5. Addressing the discussion questions. What if? As my main axis is the positive x-axis now, if I were to flip the axes, the person in my video would be going in the negative x-axis. As for how my results would change and stay the same, the velocity would still remain constant, but it would now be negative instead of positive. What does it mean? Yes, it is possible for me to say how many pushes and pulls are added together to give zero net force. There's a push from gravity as well as a push, if you will, of contact between the person and the escalator. Together, the net force is zero as they cancel each other out. Thank you for watching.